Episode 52. Can you believe it?
No, that is crazy.
52. So we now have one quarantine episode for every single week of the year. This is kind of a remarkable thing. And I want to give a special thank you to those of you who are watching live and who have watched with us every single episode up to this point. I know there are quite a few of you, and we are so happy that we've been able to share science and math with you. I also want to give a big thank you to our patrons, because could we have done this without our patrons?
Oh, absolutely not.
No, there's no way. We had to have help from Science Mom, Krista, Emily, and Liza, and we could not have paid them, and we could not have run quarantine without the support of our patrons. So to everyone who joined us on Patreon, let's say it on the count of three. 1, 2, 3. You say it too. Thank you. We are so glad that we were able to do this. Now, I want to say, before we start talking about mysteries, I want to say that endings can be kind of tough. Sometimes, especially if you are used to doing something, when that routine changes, that can be, you can have emotions of being kind of sad, maybe a little bit afraid. That's normal and that's natural. And we feel it too. Do you feel a little bit sad about quarantine ending?
I do. I mean, it's kind of gotten into the rhythm of things, and that's what life is now. So.
Yeah. We're used to spending our mornings with you, and we're a little bit sad to have it end, but we're also ready for a vacation and a break. It's time for us to have a vacation. And I feel a little nervous too. Like, what if when we start again on June 17th, what if people have forgotten about us? I kind of have that fear. It's natural to have fears and to have feelings of sadness anytime there's a big change. But we do have great things that you can watch while we're on vacation. If you've missed episodes, you can go back and watch them. We have a Math Dad versus Science Mom series on our YouTube channel. And we have a Science Mom's Guide to Water series. We'll be posting in our next Patreon post some good ideas of things that you can watch. Now, let's give some love to those who are watching live in the chat. So hello to Kyan from Montreal, to Nakia from Texas, to Roger, Science Girl, Abadu Muhammad, Kitten Boy, Marine Man,
Queen Sleepy.
I'm seeing so many comments going up. Hello to Minor Master from Delaware, to Roger Sutherland, to Graham, to Anita, to King Husky,
Megan, Marine,
Kelly. It is so good to see you guys here with us today. Thank you for joining us. Now let's start with talking about a really cool fact. The more that you know, the more mysteries you uncover. And this is one of my favorite parts about learning. So when you have a question and you start researching and you learn new things, oftentimes you uncover new mysteries. And so I want to introduce this idea by bringing up a question that we had yesterday. It was a really good question. And the question was, if putting salt on slugs kills slugs, then how come sea slugs can live in the ocean where it's super salty and they're just fine? Do you remember what my answer was?
That they're used to that so that they can deal with it.
That was kind of my answer. And I also said, well, I think they're just as salty inside as the ocean is. So then, everything's balanced. Excuse me. But then I got thinking about that. And I was like, wait a second. When you eat tuna or, a fish that like salmon that comes from the ocean, it's not salty. It doesn't taste salty.
That's true.
And so I started down a little bit of a research rabbit hole, and I found some really interesting things. So with sea slugs, it turns out that there's not really a clear-cut answer. Some sea slugs are capable of regulating how much salt content they have, and others, we don't know, we don't see that they have something that's equivalent to like a kidney that will take out extra salt and make sure that you have the right balance. But the cool thing is that you and me and all other animals, regulating how much salt we have inside of us is super important. And that's kind of the main job of your kidneys. Your kidneys are taking out extra salt and they're making sure that things stay balanced. And have you ever noticed that when you sweat, your sweat is salty, and your tears, when you cry, your tears are salty?
I have noticed that.
Yeah. So we are kind of like, we're bags of water. We have salt in us. We're bags of salty water. And that salty water has to have the right balance of salt. It can't be too salty.
So if you have too much salt, you'll cry?
No.
No.
That was not the point at all.
We're able to get rid of the salt somehow, though.
Yes, and albatrosses actually, if they're the only bird we know of that can drink seawater and get water from seawater because they fly such long distances over the ocean, and they're going to get thirsty and they need water. They can actually drink seawater, which is amazing, because what happens to you and me if we drink seawater?
Oh, it's so salty.
It's so salty. We actually get dehydrated. So if you were to drink seawater, it would make you thirstier and thirstier, and you would get dehydrated because the salt content is so high. But albatrosses, they can drink seawater, and then they have a special gland where essentially, like, they cry the saltiest tears you can think of, and they get rid of salt. They get rid of salt through this little gland kind of up by their beak. Isn't that cool?
That is pretty cool.
So those were a couple of the cool things I learned yesterday when I had a question about sea slugs and I went investigating.
So sea slugs are able to expel the salt.
Some are, and we call that osmoregulation. Some are able to do osmoregulation, but some don't seem to have that gland because they're very simple creatures, and how they do it is a little bit of a mystery. So the more you learn, the more mysteries you find. And in our handout today, we are going to talk about a couple of my favorite mysteries. And the first one is that we're going to talk about is what is matter? So if you look at this little handout part right down here, we have dark matter, visible matter, and antimatter. And matter is made out of particles. Now, when you get down to what particles are, we know that there are electrons and neutrons and protons, but what is a proton made out of?
Not more protons. It's got to be like subatomic particles.
Yeah, quarks. Subatomic particle is called quarks. And then if you ask, well, what's a quark made of? Well, a quark is made out of, I just realized we're not plugged into the Ethernet, Matt.
Oh, no. Well, I can do that. But yeah, quarks and leptons, these subatomic particles, they've got to be made of something, or do they? I mean, there's got to be some fundamental building blocks, and where do they come from? It's kind of funny because I was talking to someone the other day, and when I was 12, I knew all the answers to all the questions. I had life figured out. I knew the way the world worked. You could come to me, I knew all the answers. And now, as an adult, they're like, where did all the answers go? I thought I knew everything. And it just turns out there are so many mysteries. And yeah, what we really learn is that we understand small bits, but there are huge chunks that we don't. And fortunately, I think we have a pretty good understanding of some of the most important parts. But boy, when you start looking at the list of questions that we don't know, it's getting longer and not shorter.
Did you already talk about dark matter?
No. I just mentioned particles. Yeah, I didn't know where we were going with this.
All right. So dark matter. This is something that is so cool. It turns out that most of our universe, we estimate about 85% of it, is made up of dark matter. And we call it dark matter because it interacts with gravity. And we know it's there for a couple of reasons. Number one, we can tell that things are, like especially galaxies that are spinning, the centrifugal force should send the stars outward, but they hold together. And the only way that the math works is if there are other bigger things in there that are causing gravity to hold it together. And using math and calculating things based on our observations, we can tell that there is a lot of this material in our universe. It interacts with gravity, but it does not absorb light and it does not reflect light. That's why we call it dark matter.
It doesn't.
85% of our universe we think is dark matter, and we have no idea what it's made of.
It doesn't interact with regular matter.
There could be dark matter on top of me right now. There could be dark matter passing through Matt Dead right now, and we would have no idea because we don't know what it's made of. All we know is that it does not interact with us in the same way that regular visible matter does.
But somehow gravity is affected by it.
Yes, so it interacts with gravity, but not with the other things, which is crazy. Maybe someday one of our viewers will be the first person to discover what the particle is that makes up dark matter, or maybe it's not even made of particles, maybe it's something else. We don't know. There's some really cool things waiting to be discovered there. And then there's antimatter. So an electron has what type of charge? Type into the chat.
Oh, I know this one. A neutron has no charge.
Neutron has no charge. An electron has there's a little bit of a delay with the chat, but pretty soon we should see, there we go, negative. It has a negative charge. And protons have a positive charge. But if you have the opposite of an electron, you have a positron, a small positively charged particle. And it turns out all of our building blocks have opposites where the charge is reversed. And so we call that antimatter because it's the opposite of regular matter. So we have antineutrons, antiprotons that have negative charges, and antimatter looks like it's more abundant than regular matter, but we don't know why. And if you put antimatter and matter together, you get gamma rays, you get sort of this explosive reaction, And that's the basis of a lot of science fiction speculation, is that things are going to be powered by antimatter matter generators and reactors.
That would be pretty cool. It's really weird. You're thinking of like Star Trek episodes where they find out, oh, there's this alternative universe where they're bad guys, or this mirror universe where something else is going on. But in reality, there are these mirror particles that actually can exist. And
and some of them have been created in laboratories. So we've been able to manipulate antimatter particles in laboratories, but in terms of creating large quantities of it, like nothing like that has happened yet, of course. But it's kind of crazy.
Let's focus on the matter at hand, chat.
That's a great pun, Science Mom Jamie. So that's one of the first mystery, is what is stuff really made of? It's a fantastic question, and there are so many things that we have waiting to be discovered. Dark matter, antimatter, finding out what those things really are, what they're made of, would be amazing. And we'll get to what Math Dad's shirt means in just a minute. I saw a couple questions in the chat about that.
It's fascinating, though, because we think we have a pretty good handle. We've got our periodic table of elements. We know how they can combine, what structures can exist. But then to think that there are some more fundamental particles and more fundamental ideas going on behind the scenes, I mean, it's actually pretty impressive that we're able to understand as much as we do, considering that's only a small portion of all the matter in the universe.
All right, and now next we're going to talk about one of my favorite mysteries, and it's the one that is on our thumbnail here. So you saw this picture on the thumbnail of our video. This is a picture of our galaxy. That blue line across the middle is the Milky Way, and then on top and on bottom we have Fermi bubbles. They're called Fermi bubbles because it was the Fermi, a piece of machinery, a technology that measures gamma radiation called the Fermi telescope, was what first discovered these, so we called them Fermi bubbles. Any guesses what they are, Math Dad?
You said they detect radiation, so are they radiation?
These are huge bubbles of X-ray and gamma radiation emanating out from the center of our universe. When I say huge, I mean 25,000 light years across. Twin bubbles, one on top, one on bottom, and we have no plausible explanation for what these are.
So that this looks like an atomic blast, like in a sci-fi movie where they set off the atomic bomb in space to blow up the asteroid. Like that's the way they draw it. It blows out in a plane. And no?
Oh, like the galaxy looks like that. Well, kind of, I guess. Now let's back up and talk just a little bit about radiation. So visible light is not going to go through you, right?
I hope not.
No, like it's dark inside. It's dark inside a house. It's dark inside a room that's closed, because visible light hits a wall or it hits your skin and it stops. It does not have enough energy to pass through things. What about X-rays?
X-rays can see inside you, so yes, they can pass.
Yes, X-rays can pass through us. And if you go and get an X-ray, do you feel anything when they turn on the switch? Like if you're at the dentist chair and you hear the little buzz when they do the X-ray, do you feel anything?
Nope.
You don't feel it, but the X-rays are a very energetic type of light, and they can pass right through. And we can't see X-rays. They're invisible to us, but certain types of machines can see X-rays. We can build machines that can see X-rays, and we can build machines that can see gamma rays. Gamma rays are even more powerful than X-rays. And when I say more powerful, I mean like 1,000,000 times more powerful than visible light. These rays are incredibly, incredibly strong.
Okay.
If a gamma ray passes
through
through
Incredible
you,
Hulk, right?
So in real life, if gamma rays pass through you, you don't turn into the Incredible Hulk, you turn dead. That's what happens. Gamma rays are incredibly powerful, and they are actually something that we see out in outer space everywhere, but not in huge, huge concentrations. But anytime you have a supernova, you get gamma rays being produced, and then those gamma rays just keep going and going and going. And so you have sort of this background sense of gamma rays all throughout space, low levels of gamma rays. And that's one of the reasons why space travel is a bit dangerous. Because if you go into space and you don't have a spacecraft to shield you, you're exposed to pretty high levels of radiation. When they first discovered the Fermi bubbles, I mean, it was like, whoa. In fact, one of my favorite quotes, I gotta read it to you. So one of the leading scientists who was in charge of the Fermi telescope in this research project, his official quote on the matter was, "It just confuses everything." Like, we have no idea what is going on. So stars normally don't emit gamma rays because the gamma rays have so much energy as they're going up, they actually kind of get reabsorbed, and then they change and break into visible light and X-rays, and you end up with a lot of heat and a lot of UV light and visible light coming out of stars. So we get gamma rays from supernova, and occasionally black holes will emit some gamma rays, but nothing like, 25,000 years across big bubble of gamma rays. We think these Fermi bubbles are full of super hot plasma, and there are a couple theories, but all of the theories, they just are really weird. Like, there is no theory that you look at and you think, oh, that makes sense. Every theory, it's like, yeah, I don't think so.
Yeah, it's fun to confuse physicists.
Yep. So those are two of my favorite mysteries, but then Math Dad has some fun math mysteries for us.
Indeed.
So let's get to talking about the Goldbach conjecture, because this is pretty crazy.
Okay. So let's turn us around here. I'm singing a song, I don't know the words. I don't know the words to this song. I'm singing it loud and I'm singing it long, but I don't know the words to this song. No, I don't know the words to this song.
Oh.
All right, we want to talk about the Goldbach conjecture, but to get to the Goldbach conjecture, this is a really easy to state conjecture, but very difficult to prove, and it's one the mathematicians would love to be able to prove, and that they totally think is true, but haven't been able to prove it. So we need to talk about prime numbers in order to do this. So
if you know a prime number, put it into the chat.
Yeah. So if you have a favorite prime number, yeah, definitely list it there. All right. So what makes a number a prime number? So we're only talking about positive integers, and a number is prime if it doesn't have any other factors other than itself and 1.
Nathan says 5. Zara says 7.
7.
Those are good prime numbers.
Excellent.
Joanna
11,
says 3. Megan says 5.
2. All right.
Michelle says 2. Science Girl says 2.
So if we... Oh, my marker died. What happened?
Deepa says that you arrived. You sang it all 52 times.
Woohoo! All right. So I'm going to draw just a little grid here. So this grid measures 3 by 4. How many squares are in that grid? Well, we just say 3 times 4 is 12. Or this is actually a small enough number I could count it. So I know that the number 12 is not a prime number because I can make a grid out of it that's not just a single row or single column. So if it's a prime number, the only possible grids you can make, so like if I used 7, then I would have to make either a single row or a single column. There would be no other shape of grid that we could make.
I like that way of thinking of prime numbers.
Yeah, absolutely. And some numbers like 12 could be factored in multiple ways. We could have done a 2 by 6 grid, or the 3 by 4, or the 1 by 12. But yeah, there are multiple ways of doing that. So 12 is what we call a composite number. And yeah, composite numbers are not prime, whereas we got these prime numbers here. Is the number 1 a prime number? No, it is not. So no, number 1 is kind of special. We don't say that it's a prime or a composite. It's just a unit. It's something that has a multiplicative inverse. But okay, so prime numbers are super important. They're kind of the building blocks of math. So in chemistry, you've got your building blocks, you've got your elements, and they can combine in certain ways. In math, our building blocks are prime numbers. And those prime numbers can be built to get any integer you want. So in fact, the fundamental theorem of arithmetic says that you'll be able to take any number and factor it into primes or products of prime numbers, and that will be a unique factorization as well. So
whoa. Well, maybe just keep going. You lost me there just a little bit. Are you going to come back to it?
It wasn't super important to what we're talking about today, but if I have any number, so let me just pick one, 24, I can write that as a product of prime numbers. So in this case, 24 is 2 times 2 times 2 times 3. So I've been able to break 24 into prime numbers So this is its prime factorization. So there's 3 2s and a 3, and that factorization is actually unique. There's no other way of breaking 24 into prime numbers. And there are number systems where that's not true. Maybe the factorization isn't unique, or maybe it can't factor into primes, or you've got to really appreciate that this is something special that the integers have. And it's easy to take it for granted. Okay, at any rate, we now know what prime numbers are, and you'll be seeing them a lot more if you haven't already.
And I have to say, I think our favorite prime numbers in the chat have been 2, 3, 5, 7, and 13. Those have been the ones I've seen the most often.
All right, kind of makes sense that we'd like the small numbers. Yeah.
And a couple people pointed out 2 is the only even prime number.
That is true. It is the only even prime number, and it's also the smallest of our prime numbers, the least of all of them. Okay, so what is the Goldbach conjecture? Well, the Goldbach conjecture, I'm gonna write this out. Goldbach.
When Math Dad first told this to me, I thought he said Goldbox or Goldilocks. I was like, a Goldilocks conjecture.
Yeah,
really? That sounds interesting.
She kept writing it down wrong. It's kind of funny. Okay, the Goldbach conjecture says that every even number greater than 2 is the sum of 2 primes.
Every number bigger than 2 is the sum of 2 primes?
Every even number that's greater than 2 can be written as the sum of 2 prime numbers.
Whoa.
So let's verify this. See if this is possible. Let's even start. Let's go 4, 6, 8, 10. All right. So 4. Can we write 4 as the sum of 2 primes? Help me out, science mom.
2 plus 2.
2 plus
that one's
2.
Easy.
6?
3 plus 3.
Okay. 8.
5 plus 3.
Okay. 10?
7 plus 3.
Ooh. Or, I bet some of you might have been thinking 5 plus 5. So this is not a unique, there's no claim of uniqueness here. And let's do a few more as a sanity check. All right, 12, 14, 16,
All right, so
18. All right.
12 could be, I was going to say 11 plus 1, but 1's not prime.
1 is not prime.
1 is not prime.
So how about
9 plus 3?
9's not prime.
Well,
7 plus 5 will work. It's 14.
14. 7 plus 7.
Okay. 16?
16. Check in the chat. 13 plus
13 plus 3 would work. All right. And then 18.
13 plus 5.
13 plus 5 would work. So there are probably other ways of doing it. So we're not claiming that every number can be written uniquely as the sum of 2 primes, but that there will be 2 primes that sum to be any even number except for 2. 2 is just too small. But
so at this point, I'm saying, all right, I totally believe you, Math Dad. This makes sense. Why is it a mystery?
Well, mathematicians, when they try to prove something, it's actually a little bit different than in the other sciences where, oh yeah, we proved this. Really what they're doing is just showing, in most sciences, they're just able to say, oh yeah, the evidence matches up. We're running these tests. We're able to eliminate the hypotheses.
So in math, this does not count as a proof.
That is correct. Well, and notice we only checked 8 numbers here. Every even number. How many even numbers are there, Science Mom?
Infinity.
There are infinitely many even numbers.
Whoa.
Guess how long that would take to check?
Forever?
Yes, infinitely long. At no point in time could you have possibly checked all even numbers. So when mathematicians are trying to prove something, there are a couple ways of doing it. If we wanted to prove that this was false, all we would need is one counterexample. If we could find one even number that could not be written as the sum of 2 primes, that would disprove this conjecture. So when we say a conjecture, that's just it's maybe stronger than the word guess, but it's an assertion. We're saying, I claim that this is true. I don't know how to prove it, but I think it's true, by golly. And okay, so that it's kind of like the gauntlet has been hurled. Like, oh, can we do this? And a lot of mathematicians have tried unfortunately, we just don't have very good tools to tackle this problem because prime numbers, the primeness of a number is a multiplicative property, right? It doesn't have anything to do with addition and subtraction beyond just the multiplication means repeated addition. So here we're adding two primes, and boy, that just doesn't give much structure at all. So we're messing with an additive structure on numbers that are defined based off of their multiplicative structure, and somehow we're trying to combine them, and there are not a lot of good tools or ways to answer this. So one thing we can bust out though is get out the computer. We try. We say, all right, let's test, and we just go from one even number to the next even number. Let's check it. Ooh, that one didn't work. How about the next one? How about the next one? And we still haven't found a counterexample, and they have checked a lot of numbers. So like up into probably into the trillions by now.
Wow.
Yeah, it's that's a lot of even numbers to test. So what does the evidence show? Well, it turns out as the numbers get bigger, they get more and more pairs. So yeah, if I picked the number 100, my guess is that there are probably 5 or 6 pairs of prime numbers to add up to be 100. And the higher we go, we're getting more and more pairs, but it's not climbing uniformly. Sometimes there are more, sometimes there are less, fewer. And because of that, it's just not clear. How do we know that there's not just one really big number where it just turns out there aren't 2 primes? I don't know. I think pretty much all mathematicians think this is a true conjecture, although we don't have any great way of proving it. So this is an example of a famous conjecture made by Goldbach, and we don't know how to prove it. So this is an example of a mathematical mystery that we don't know how to solve. So
I've got a question for you. What is the hailstone sequence?
Okay.
Do you know what the hailstone sequence is?
Yeah, we're going to talk about Collat's conjecture next.
Okay, but first, I think we should go slightly out of order, and I think we should share a couple slides right now.
All right, let's do this.
So our art prompt for today and for yesterday is to draw your favorite moment from quarantine. And this Science Mom Liza drew that. Isn't that a cute cartoon?
Aww.
I love it. So it's the dry ice bubble, the dry ice episode. And so we're going to showcase some art today. And then if you want to share your art and send it in today, we'll also showcase some tomorrow when we do our game show. So let's share our screen, and we'll just share 5 slides right now, and then we'll do more at the end. So favorite moments. This one is from Juniper, and she is Team Math Dad Song all the way.
Woo.
Her favorite is the song. I can't believe it.
Like I said, that I don't think there's anyone who dislikes the song. There are just some people who like it too much, and it gets stuck in their heads, and they.
Oh, so I like it too much?
It's okay, Science Mom. You like it too much, but be strong.
And then in Science Mom Amber's family, their favorite was the paleontology episode with Ashley Hall, that Chat with the Science episode. Isn't that a fantastic drawing?
That is so impressive.
And I've seen some great coffee ground fossils that people made as well from those.
Oh, nice.
Graham's favorite moment was the what's in the bag where the answer was a shoe. So what has a tongue but no mouth? And it's like, whoa, what is that? A shoe.
Yeah, that was a good one.
Addison's favorite was the dry ice and Math Dad's song.
Woo-hoo! Go Addison.
Haley loved the volcano.
Yeah, that was fun. A little
A
scary.
lot of fun.
But yeah.
And first chatting with a scientist, when the Extend-A-Grabber, we had that challenge and you were trying to knock the ping pong ball out of my Extend-A-Grabber. Do you remember that?
Yes. I was going to win that competition.
So that was quite a bit of fun too.
All right.
And now our next conjecture is, you said the Collat's conjecture?
That's right.
All right, so now we have a second math mystery, and I think we should mention the Millennium Prize, because how many Millennium Prize questions are there still?
So the Clay Institute in the year 2000, so the millennial year, came up with prizes, $1 million prizes to anyone who could solve these 7 problems. So if you solved one problem,
you got
$1
$1
million.
million.
And unfortunately, those problems are not as easy to state or to understand the Goldbach conjecture here. I think I can explain that to you, and you can understand it. You might not be able to answer it, but at least it's a very understandable problem. Some math questions, they take years and years of study just to even understand what the questions are. So the most famous unsolved problem in mathematics is called the Riemann hypothesis, and it's famous.
And is it one of the Millennium Prize?
It
questions?
is.
So $1 million on the spot if you solve the Riemann hypothesis. And there were 7 of these math problems, and a couple of them have been solved. And you didn't have to like submit it somewhere official. You just like one of the people who solved one, they posted it online and they said, well, you won $1 million. Do you want it? And the guy was like, nah.
Yeah.
Like there was one person who actually turned it down, which is kind of.
Yeah. I think that's the only one that's been solved so far. But yeah, there are some big questions, and they are not easy to solve, as you can imagine, because if they were, you'd easily get your $1 million and you'd move on. But so yeah, it's important to understand. Some questions are so tricky to even understand what the question is that it takes a lot of study. So if we spent an entire episode on just the Riemann hypothesis, I think we might be able to get a decent understanding. It kind of depends on the age group, but it involves complex numbers, which are not nearly as bad as they sound, but at the same time, it's just not something that we have much experience with.
But yeah, several of these problems, when I look at them, I can't understand them. I can't even understand what the problem is. And so then having to answer it is a whole nother step. They're really complex.
Yeah. Well, I don't understand some of them. So.
And you have a PhD in math.
I do. So yeah, you'd have to do some serious studying to come up with answers. All right. So the Collatz conjecture, it's also called the 3n plus 1 conjecture. And so it's formed by applying one of 2 rules repeatedly. So the first rule is, let me change that. So double any odd number. I can do this.
Are you sure?
That was not right at all. All right. So if n is odd, then the next number is 3n plus 1. So we multiply the number by 3 and we add 1 to it. And then the other rule is if n is even, then the next number is n divided by 2. So we're dividing the even numbers by 2, not multiplying them by 2. So we're going to use these 2 rules, and we're going to generate a sequence of numbers from it. So let's just pick a number and see where it leads us. So if I start with the number 5, I'm going to apply one of these rules. So 5 is odd, so I'm going to replace 5 with 3 times 5 plus 1 more. So 3 times 5 is 15, plus 1 more is 16. All right. Now 16 is an even number.
So I divide it by 2 and get 8.
Okay, 8 is even.
Divide by 2, I get 4.
And
divide by 2, I get 2. Divide by 2, I get 1.
1, okay. 1 is odd, so then if we kept going from here, we'd multiply by 3 and add 1. So 4, 2, 1, 4, 2, 1.
And then you just get 4, 2, 1
just
forever.
Keep repeating, 4, 2, 1 at that point. All right, let's try another one.
So this is kind of cool, but it seems to me like someone's just playing with numbers for fun. Is there a point to the Collatz conjecture? Or is it just sort of a fun idea with numbers?
I can't actually think of any strong application on this.
Will you tell the story real quick about your college professor who when you asked if it was applied, what he said?
Yeah, okay. So
tell the story really quick. This is a funny story.
In Calculus 2, you learn about what are called Taylor series, which allow you to use these polynomials to approximate these complicated curves. It sounds really fancy. It's not too bad or too fancy. At any rate, though, so at one point, a student raised his hand and said, "All right, so when would you ever use this? Or what Yeah, what good is? When would you use this?
So, and that's a good question. So they're in a math class, and one of the students asked, "Could you tell us when we'd ever use this?" And here was the answer.
Well, but this. So he asked that after saying this is the most important mathematical discovery of the millennium, the coolest tool we have. So the student asked, "Well, when would we use this?" I said, "Well, suppose you were trapped on a desert island, and aliens landed, and the only way they could get their ship to fly again was if they could calculate the sine of 44 degrees accurate to 7 decimal places, and you didn't have any paper. You could only write in the sand with your fingers, and then it would get washed away every day." And so at any rate, he invented this crazy convoluted situation, and basically what it meant was you'll never use this. At least not directly in the way that we were doing it in the class. Although it turns out, I mean, it does get used all over the place. Although now in the day and age of calculators, it gets used a lot less. Or I mean, it's often the calculators themselves are using this behind the scenes. So not all math has a lot of practical applications. And this would be an example of that. There is no physical problem in the real world that says, oh, as soon as we could solve this, we would then know how to build a machine that would accomplish some task. That just doesn't exist.
So back to the Goldbach's conjecture, it's saying that if you have a number. Let's
do one more. Yeah,
okay.
I haven't said what the conjecture is, but let's see if we can understand the sequence. So what if we started with 6?
That's even.
So
we divide it by 2 and we get 3.
3. All right. 3 is odd, so we multiply by
3 times 3 plus 1 is 10.
Okay, good. Multiply by 3 and add 1. All right. 10 is even.
Divided by half and we get 5.
5. Oh, we'd already done this one. So what's after 5? We know we're going to get 16, 8, 4, 2, 1, and then it just keeps repeating. Okay, so interesting. What is the Goldbach's conjecture? And what they call these hailstone sequences. So somebody in the chat had mentioned that name. Okay, so the Goldbach's conjecture says that no matter what number you start with, if you follow this procedure, you will eventually get to 1. And then, of course, if you get to 1, then you're going to get 142, 142, 142. And this is an unsolved conjecture. Is it true? Well, hard to say. Is it harder than the Goldbach conjecture? Boy, turns out we don't have very good tools for solving a problem like this. There is some strong evidence that seems to imply, that's most likely going to be true because on average, these numbers seem to be getting smaller, and there is some evidence supporting it, but that doesn't mean that we couldn't have a counterexample. Maybe there's some little loop of numbers that just goes around and around forever and never gets down to 1 because that loop itself is a repeating loop.
Ooh.
And we haven't found it. This one is a lot easier to check by a computer because the computer can just follow this procedure. It turns out factoring numbers is hard, even for a computer. And that's why your credit card, debit card PIN is safe. It uses these really large prime numbers that have been multiplied together to use what they call the RSA cryptography. And this, if it was easy to factor big prime numbers, then public key cryptography would not work, and they'd be able to get your PIN and
You're telling me the reason we can use credit cards is because of prime numbers.
It's because of prime numbers, because prime numbers are hard to factor, especially big prime numbers.
That's pretty cool.
Yeah, which makes it really interesting to think of, wow, what happens when we get quantum computers that actually can handle numbers of that size? And in that case, we might have to come up with some different method of doing public key cryptography, or to pick prime numbers that are a heck of a lot bigger. At any rate, though, so this Goldbach's conjecture has been checked out to some ridiculously large number, like 10 to the 60th. I almost don't believe how big that number is that we've checked. but it's much easier to check because you're just looking at 3n plus 1 and 2 and n divided by 2, and they could just calculate that over and over again. And also, as we saw here, if you find a number at some point that we already know the answer to, it's part of another sequence, well, then we don't need to keep going.
Science Mom Jamie has another fantastic pun here that we can use our credit cards on Amazon Prime.
I'm sure that's why Amazon named it Prime.
Amazon Prime, yep.
That's right. In honor of the RSA algorithm. I like that. Okay, so and just another example of a question that's very easy to write out, but that is
very difficult
very
to answer.
difficult to come up with a proof of. So, yeah, and math is full of these, although a lot of them, as we said before, are not so easy to understand what is going on. So on this one, unless you've got a supercomputer, you're not going to be able to find a counter example because all the easy ones have been checked. There's no low-hanging fruit on this question anymore. But if we could find a single counter example that would disprove the conjecture, and to prove the conjecture, you'd have to come up with an argument that works for every real number, or every integer. And how many integers are there? There are infinitely many.
Infinitely many.
So we do this all the time in math. We're able to prove such things, but yeah, this one seems tricky. We don't seem to have the tools available to us. All right.
Are you guys ready for fact or fiction?
All right, fact or fiction time. Science Mom. So true or false? If the sun were made of bananas, it would be just as hot.
Whoa! If the sun were made of bananas,
yes. So
it would be just
a magician
as hot.
casts a spell right now and replaces the entire mass of the sun with a mass of bananas.
So a bunch of bananas just as big as the sun. I'm going to say true, because if you have anything that is as big as the sun, I think the force of gravity will bring it in, and then you will start to get fusion. And then once you have fusion, atoms combining together, you're going to get a star. It might be a different type of star if it has heavier elements, like you're going to have potassium and not be made of hydrogen and helium. That's kind of my guess.
Okay, so although, you're right. So a couple misconceptions.
All right,
we're
I'm glad you're going to correct me, because I'm seeing Anne and Saganya and Megan, Elliot. I'm seeing lots of trues here.
Okay, so I didn't say the volume would be the same. I said the mass would be the same. So you're replacing. So obviously gases are expanded much more than bananas are.
Yeah.
But okay, so we're replacing the mass of the sun with the same mass of bananas.
Would be much smaller.
Yeah, okay. It would end up being smaller because they're more compressed, at least with this initial replacement.
Yeah.
Okay, then the pressure is what would cause this heat. Would fusion get going? Yeah, to some extent. There's some water in the bananas, and you really need the hydrogen gas to get that fusion going. So it wouldn't stay as hot. It would cool down because you wouldn't be able to get the same level of fusion reactions going.
Gotcha.
But yeah, at least at first it would be just as hot because the same mass would cause the same pressure, and
wow,
yeah, put out a lot of heat. So I read that, I was like, nah, is that true? And I had to research it.
It is true.
It is true. All right, true or false, Science Mom? Prime numbers help cicadas survive.
Ooh. I was just reading that this year is actually a 17-year cicada year. Like, we should have those 17-year cicadas come out. And I know that 17 is a prime number. Help me out in the chat, you guys. Deepa says true. I'm going to go with true. McCrae family says true. Anne says true.
Triple true there. All right, Anita. All right. Yes, this is a true.
So explain how. How does this work? Okay,
so cicadas are either on a 17-year cycle or they're on a 13-year cycle. They're different geographical regions with different families that are on some different cycles. I think across the United States, there are about 15 different geographical regions. And yeah, some of them are indeed happening this year. So what's going on? Why in the world would they wait 17 years to come out and breed and do whatever it is they do and then go back to hibernating for 17 years? It's because, at least in part, predators, they're not going to have a lot of natural predators
if they all hatch at once.
That's right. They're not reliably there, so there can't be some animal that depends on them and only eats those. So nothing is going to specialize in eating just cicadas, although when they come out, they are a very popular food for just about everything.
Now, I saw Akiko asked, what's a cicada? We should say, for those who have not seen cicadas before, I'll draw you a picture real quick. So cicadas are an insect, and they spend a lot of their life, most of their life, they spend underground as a larva. And their underground larva body, oh, that's our black marker
there. That's the
bad one. Their underground larva, they've got their little legs and then a little body, little head. So it's not a very good drawing, but when they're underground, they're just sort of, they're eating detritus and things. And then when they come out, they actually will crawl up and then they'll hatch out of their body and go through metamorphosis. Now, when a caterpillar turns into a butterfly, you don't really see like the remnants of that. But when cicadas hatch into their adult form, they leave behind a shell with a little crack down the middle. So you'll find these little shells all over trees and logs and things where they crawled up out of the ground and then went through metamorphosis. And now they are a little bug that has a big pair of wings. And they make this buzzing sound that is so loud. And we hear it all summer. So most summers, we have cicadas in southern Nevada where we live, and most summers we'll have a few cicadas around. But this year we might have a lot more.
That's right. Okay.
So, and when I say there's 17-year cicadas, most of them will come out on that 17th year, but every year there will be a couple. And I don't know if they're a different species or if just some of them didn't get the memo and they're not synced with the rest of them.
That's true, because we actually don't know how they're counting the 17 years. I mean, I couldn't count 17. You put me underground. It's like, all right, has it been 17 years? I couldn't do it.
Yeah. And Blanca and Jody and Owen, several other people are saying the sound is so loud. It's so annoying. It's really, really loud. And if you've never heard it before, you should just Google cicada, and I'm sure some videos will pop up online, and then you can hear that just loud, constant sound.
That's right. But so if there were some predator that could rely on them, so if they came out every year, then
there would be birds and other insects.
Fewer of them, it'd be harder to reproduce. All right. Well, what if you go every 2 years? Well, in that case, then the predators might starve during the off year, or there might be fewer of them. So there's some advantages to waiting more than a year. But every 2 years, maybe the predator will just wait every 2 years and come out. Well, there's something cool about 17. 17 is a prime number, or 13 is a prime number, and those are the two intervals that we find with cicadas. Well, if no predator is going to wait 17 years for its next meal, to come out or reproduce. But so even if they picked 2 years or 3 years, 5 years, 6 years, some smaller number, well, how often is a multiple of 6 also a multiple of 17? Well, it turns out that's every 102 years. So that's pretty good odds in favor of the cicadas, and pretty bad against any predator for them. So by waiting a prime number of years, it makes it very, very hard for any predator to specialize and focus on them.
That's pretty cool.
Yep. So prime numbers.
Go prime numbers.
Bailing out those cicadas. All right, Science Mom. Fact or fiction? Spelling out the numbers from 0 to 999, you won't use the letter A at all.
Spelling out the numbers from 0 to 99, you won't use the letter A at all?
0 to 999.
999, because 1,000 has an A in it.
1,000 has an A in it.
And are you telling me all of the other number names below that don't have an A?
I'm asking you whether it's true or false.
Okay, I'm thinking. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Just going to count to 1,000 for us right here, live on this show.
20. I'm saying it's true, because I am not thinking of a number that has an A.
It is true. It's a true fact. Yeah. So if you think about the base digits, so yeah, 0 up through 9, if you go through those, none of them have a letter A. And all the other numbers are actually just based off of those base digits in a way that doesn't give any letter A's. So in other languages, I just probably wouldn't translate very well, but in English, the letter A does not show up from 0 up to 999, or in other words, the first whole number that has the letter A in it is 1,000.
That is pretty cool. I want to give a quick shout out to Nathan Rosales, who in the chat today was asking everyone if they were going to the rocket launch. Did you know that there is a rocket launch today?
Is this SpaceX?
Yeah, this is pretty exciting. So SpaceX is launching a NASA rocket, and if the weather goes well, it's going to be broadcast live at 11 a.m. and it's going to be for free. You can watch on YouTube. It's going to be lots of places. So
when the cicadas go out into the world, They'll be in
They'll
their
be
prime.
in their prime. That is a great joke, Science Girl. Nicely done. And then Krista, someone asked, what does it sound like? And it is kind of hard to describe. She says it's like a buzzing sound and kind of like a clacking.
Almost
and
like an alarm.
Yeah, I agree. It's definitely something you would want to Google and hear because it's a sound that I cannot reproduce.
No.
Yeah, and it's very, very loud.
Yeah, and confusing too. Like, what is going on?
Yeah. So, and the time for the rocket launch is 11 a.m. I believe. No, not 11 a.m. So it's 4:30 Eastern.
1:30 Pacific.
1:30 Pacific. There we go.
So
4:30 Eastern.
4.5 hours from now.
Yeah, 4.5 hours from now. Quite exciting.
Yep.
All right. We have a few more slideshows to show, and we also have a math mystery. Let's do your.
We'd better talk math. All right. So if you look down at my shirt here, what you're seeing is an extension of the game Paper, Rock, Scissors, and I think most of us have played
rock, paper, scissors.
Rock, paper, scissors.
Yeah.
That's probably the typical way of saying it. All right. So real quick, Science Mom, game of rock, paper, scissors on 3.
All right. Well, who wins? Like, there's got to be a prize, right?
So you give me a kiss if I win, and I give you a kiss if you win.
You know, there are Oreos on top of the fridge. How about whoever wins gets to eat all the Oreos?
There we go. Okay. All right. So rock, paper, scissors, shoot. Okay. Nope. It was a tie. We both did scissors. All right. Rock, paper, scissors, shoot.
Oh, man.
Rock, paper, scissors, shoot. Oh, scissors beats paper there.
Man, that gets the Oreos.
So my guess is most of us have played that at some point in time. So this is an extension where instead of just having rock, paper, and scissors, we have lizard and Spock. So we got lizard here and Spock are the other 2 hand signals that you can show. So
when we add this in here, come a little closer. So the lizard is going to eat the paper. It gets crushed by the rock. It gets decapitated by scissors. It poisons Spock. And then Spock smashes the scissors because he's a Vulcan and he's very strong, vaporizes the rock, Vulcan powers again, is poisoned by the lizard. The paper disproves his logic, so paper defeats Spock. And that's how it works. So it's a little bit trickier to keep track of, but it all works so that now you can play rock, paper, scissors with more people. Right.
Well, it does make it a better multiplayer game. I think it's more fun. But okay, let's actually try this though. You and me, Science Mom. All right. So now we're playing rock, paper, scissors, lizard, Spock.
All right.
Rock, paper, scissors. Okay. So I got
lizard.
Who,
I got Spock. So
that was Spock. Oh, I thought you were paper.
Yeah. No.
Oh no, you decapitate me.
No, I don't.
No. Oh, I poison you.
I
poison you. That's right. What? Oh, that was the scissors. Okay.
Yep.
All right. Here again. Rock, paper, scissors. Okay. Got
it.
Think.
Spock smashes the rock.
That's right. Vaporize the rock. So yeah, it opens up some new possibilities. So the question that I wanted to ask you guys is, why did we introduce 2 new things? Why not just one? Why not just add a lizard? And it turns out it doesn't work. Why wouldn't it work to add just 1 additional piece? And
I bet the answer has to do with math.
I bet it does, indeed. So we saw this diagram here. This is actually what they call a digraph. So it's a directed graph. So there are lines between everything, but they're directed lines with those arrows because one thing dominates another. And yeah, if you try this with just 4, something goes wrong. Something is imbalanced. And I'm going to let you guys think about that. And I actually, for my math mystery challenge today, I actually wanted to ask you guys to expand rock, paper, scissors, lizard, Spock to
add 2 more.
Add 2 more. So you're going to get 7 items in total. So can you extend it in a way that keeps all these same rules intact, but that is also nicely balanced? We don't want one super item that defeats everything, because that of course would not be a very fun game. So yeah, we need a balanced game where each thing has an equal probability of winning or losing. And yeah, so can you guys come up with 2 more objects?
Kimberly wants to know, where did you get this shirt? We got it from $6 t-shirts, not a sponsor, but they've got cool shirts.
Yeah, it's a website. It's called $6 shirts. Okay.
Yeah.
Yep. So yeah, so this game's been around for 18 years now. And yeah, my roommates and I were in college, which would sometimes play it. So
that's a fun one. All right, before we finish with our slideshow, I want to share another quick little story about internet safety that I think is kind of funny. So, Math Dad, do you remember this?
Was this the birthday girl?
So that picture is actually a stock photo called Girl with Dog. It's a stock photo, but and this is sort of funny. Someone sent it to us and said, "My daughter Leslie has a birthday. Will you please sing Happy Birthday, Leslie on your show?" Or, tell her happy birthday shout out. So I replied back and said, "Well, yeah, we do birthday shout outs for patrons." And then they replied back and said, "I signed up on Patreon, only they didn't." And at this point, that should have been like a little red flag to me. But I was like, might as well make someone happy by singing them birthday. But yeah, we said happy birthday to a person who does not exist, to a stock photo.
Yeah.
Now,
not the worst mistake I've ever made. But
now I will say real fast, because I know we have some true fans here. If you recognize, who it is who on Facebook has been posting like fake pictures and things, don't go after them and try and dogpile on them, because we don't know who it is. It's possible this could be a person, an old person who is cooped up in a nursing home that's totally on lockdown, and they're just bored out of their mind, and maybe this is how they're entertaining themselves. We have no idea. But
we did get fooled. So somebody over the internet misrepresented who they were, told us, "Oh, I'm a parent of a child who loves your show." And yeah, it turns out we believed him. And in this case, no harm done. We said happy birthday to a stock photo. Yeah. Yes. But we have taken time to do just a couple internet safety lessons. And I have to say, we've covered some amazing things, but I do hope that one of the things that will stick with you is to take your privacy seriously when you're online. You may feel like you know some of these people who you see in the chat regularly really well because you've been chatting with them every day, but you do need to be careful to make sure that there are certain things you protect. Your address and your location and your real name, those things you want to keep safe. And then it's good to just kind of have a little bit of common sense, where if a little red flag like that pops up, where you know that someone lied to you online, that you don't want to pursue that relationship further. It's time to do a boundary. Yeah, it makes sense. Life is short. We should be striving for more genuine relationships, and yeah.
Remember our internet safety tips. So, and I know that in the chat, you guys have been so good the last couple of weeks to not try and share email addresses or things like that. But yeah, keep yourself safe online. And now let's finish with our slideshow. Yeah, I'm really, Math Dad and I think it's pretty funny about the whole happy birthday to a stock photo thing. Science mom Krista was like, "Oh man," she was not so amused. Like stinker pants people. All right, here we go.
Oh.
So Rishabh, favorite lesson was the one on photosynthesis, which is one of my favorite topics as well. And favorite math lesson was prime numbers.
Woo.
Great drawing there.
No. Well, this isn't prime numbers. This is binary numbers.
Binary. Yeah, that's what I meant.
You've got prime on the brain here today.
I do.
Yeah.
Binary.
I love binary numbers.
Yeah, even better than prime numbers. And then Isla, her favorite episode was the one about pets. And look, there's the bearded dragon on Math Dad's shoulder, and our guinea pigs and the desert tortoise, and the parrot on the screen. That was a fun episode. I enjoyed that one too.
Me too.
And then Ava did these incredible drawings.
Whoa.
So there's the song.
That actually looks really accurate. I
It totally does. And the goldfish shirt.
I think she left off my hair, but about
that's as much hair as you have, Math Dad.
Oh, but she likes the song. And okay, this was the Minecraft maze.
Yeah. And then the fiery volcano. Love this one. And then Thea did her favorite episodes were the poop episode and the slugs episode. So yeah, the wastewater one is one of my favorites too. It's just a fascinating topic that most people don't spend a lot of time thinking about.
It's easy to take for granted.
And I love the gastropod episode too. Ivan's favorite episode was the floating letters. Do you remember that?
No.
So draw with a dry erase marker and then you pour water on the plate and they float. It's a super fun science investigation. If you guys have dry erase markers, I highly recommend it.
Yeah, I can't believe that works.
Yeah. And then Chelsea was painting with Math Dad.
Ooh,
so now you do have hair.
That's right. I just need a blue wig, and then I'm
That's
set.
right. And then we had some great little slugs made yesterday, and some great pictures on Facebook of people racing them and having fun racing. And then from our painting with the scientist, we did the nudibranch, not nudibranch,
Yeah.
nudibranchs, and some great artwork with the nudibranchs.
I like it.
And we will, so we should talk real fast about tomorrow. So tomorrow we are going to have a game show, and I want to give a thank you to everyone who has submitted questions. We have a great collection of questions, and it's going to be interactive. You will probably want to have either like 2 browser windows open or like split your screen.
Okay, so you'll have 2 options. You can just watch the show like normal.
It's true. And you can comment in the chat with your answers.
Or if you have a separate tab would work, or a phone, I'm going to give you a website URL where you can actually vote on the answer each time. And yeah, so we'll be able to display what answer people are giving. So it'll be kind of just a quiz where we're going through some fun science topics. Most of the questions come from things that we talked about here in the show, although several people brought in new topics that, I didn't know that was true. So yeah, this will be a fun adventure. We'll see how it goes. And so you can participate either way. We'll give you a link where you can submit your own answers as you go, or you can just watch and see what everyone else says.
Yep. And I want to end with kind of my favorite thought, but I also want to remind everyone that we will be back June 17th. So end of quarantine does not mean end of the Science Bomb YouTube channel or end of seeing us. We're taking just a short vacation, and then we'll be back on June 17th with more science videos for you over the summer. But I'm going to end by sharing my favorite thought that I shared at the beginning. So this is just kind of my favorite thing to think about sometimes when I want to just kind of sit back and reflect. Have you ever taken a minute to consider that you are a human being, that you exist, and you are not a rock or a lizard or a piece of paper or Spock? You are yourself. And when you consider the world around us, something as simple as a pen. A pen is pretty simple, and I can buy one for just a couple dollars. But if I was by myself on a desert island, in the rest of my life, I would not be able to recreate a pen. I don't know how to make plastic. I don't have the skills to mine the metal to make this or to make the ink. We are part of a human family, and that is an amazing thing. We're able to communicate across space and time. You can read words written by people who lived hundreds of years ago and understand what they were thinking. And this is incredible. And I want to end by just saying thank you for being part of our family and joining us to learn about science the past 10 weeks. It has been wonderful.
Bye.